quantum solitons, trapping matter waves that defy reality. Hey there, curious minds. Imagine waves of pure matter zipping through space without ever falling apart. Not light, but actual particles behaving like unbreakable packets of energy. That's the wild world of quantum solitons and stable light packets we're diving into today. Buckle up, because physicists have just cracked something mind-bending. Let's start with the basics you might know from school. In quantum physics, particles aren't just tiny dots. They're described by wave packets, short bursts of waves that act like localized blobs of probability. Erwin Schrödinger dreamed this up in the 1920s to bridge quantum weirdness and everyday reality. A wave packet is a superposition of plane waves, all different frequencies and wavelengths smooshed together. The peak of the packet moves at the group velocity, which for particles is p/m, momentum divided by mass. That's exactly the classical speed of a particle. Cool, right? It means quantum waves can mimic bullets or baseballs when you zoom out. But here's the catch, and it's a big one. Normal wave packets spread out like wildfire. Picture dropping ink in water, it blurs fast. Heisenberg's uncertainty principle guarantees it. The narrower your position certainty, delta x, the wider your momentum spread, delta p for a supertight packet, say with delta x of sqrt, a /2, it spreads with velocity h bar over m sqrt, 2a. In the time it takes light to cross an atom, that packet's unrecognizable, smeared across the room. Physicists once thought, no way these represent real particles. They disperse too quick. Enter the game changer, stable wave packets. These aren't your grandpa's dispersing blobs. Researchers have derived a precise uncertainty principle that's 6 times stricter than Heisenberg's for 3D systems. In one dimension, they use hidden variables, imaginary ones like x that make the phase oscillate perfectly. These packets stay coherent because their width sigma depends on conserved momentum and energy, triple guaranteed by spacetime symmetry. No spreading. Ever. It's like a wave that laughs at dispersion. Now, solitons crank this up to 11. Solitons are self-reinforcing waves that maintain shape forever. In quantum terms, matter wave solitons are waves made from atoms or particles that don't disperse. Light solitons, stable light packets. Think laser pulses that hold together through nonlinear effects, zipping without blurring. For light and vacuum, the dispersion relation is linear. Omega equals ck phase velocity equals group velocity. Both see no spreading for light pulses. But for matter, dispersion relation is omega equals h bar k squared over 2m quadratic. Packets bloom like flowers. Physicists are trapping these now. In labs, they've created Bose-Einstein condensates, clouds of millions of atoms cooled to near absolute zero, acting as one giant quantum wave. Laser traps hold them, and boom, matter wave solitons emerge. These solitons propagate at group velocity d omega over dk, matching classical particles. Yet they solve riddles like wave packet reduction during measurement. When you observe, the packet collapses because phase velocities in propagation direction outpace the transverse plane. Hidden variables kick in, stabilizing the crash. Surprising fact, these stable packets predict antiparticles naturally, like in Dirac's equation from 1928. But they fix his conflicts with better wave solutions for particles and their opposites. Photons quantize perfectly here, equations 8 and 9 nail it. And get this, phase velocity can exceed light speed horizons. Beyond c, in that weird space, reduction happens. It's not faster than light travel, it's math unlocking quantum secrets. Flash to lasers, the tech exploding today. Laser technology powers everything from eye surgery to fusion reactors. Stable light packets are key. In fiber optics, solitons carry data terabits per second without distortion. Nonlinear optics balances dispersion and self-phase modulation. The pulse pulls itself tight. In 1980s experiments, they sent soliton signals 10,000 kilometers without repeaters. Now, quantum solitons promise unbreakable quantum networks. Obscure gem, if sigma quantizes from an atom's emission, the packet's perfectly stable. No decay, coherence measurable, tied to initial conditions. Not always Gaussian, could be square or wild shapes, and for zero-energy waves, infinite wavelength, they freeze, no change, eternal. Matter wave solitons? They're being trapped right now. In 2023, labs at MIT and Vienna, teams used optical lattices, egg crate laser grids, to pin rubidium atoms into soliton trains. These trapped matter waves oscillate stably for seconds, defying entropy. Numbers blow minds. One experiment sustained a soliton packet over 100 micrometers at speeds of 1 millimeter per second, with uncertainty product just 0.1 h-bar, crushing Heisenberg limits. Why care? This bridges quantum to classical. Wave packet centers follow Ehrenfest theorem, classical paths exactly. Quantum fuzz fades at macro scales, but solitons hint at new physics. Perfect quantum computers from non-spreading qubits or gravity waves as stable matter packets in curved spacetime. Imagine swarms of soliton drones, self-healing lasers cutting fusion fuel precisely, or medical lasers zapping tumors with pinpoint-stable beams. Trending now, quantum sensors using these for earthquake prediction, sensing shifts nanometers away. We started with spreading waves, ended with unbreakable matter bullets. But here's the mind-blowing kicker. In these stable quantum solitons, physicists have trapped not just waves, but actual matter behaving as light-speed phase packets, hinting particles might be eternal solitons surfing hidden dimensions, never truly born or destroyed. What reality are we even in? Chew on that till next time.